My name is Joshua Fitzgerald. I am a PhD student in the Engineering Mechanics program at Virginia Tech, and my advisor is Dr. Shane Ross. Today, I will be presenting a new theory of low-energy transit orbits in the periodically perturbed restricted three-body problem. To understand the theory in the periodically perturbed case, it's a good idea to first review the theory in the unperturbed case, which is the classical circular restricted three-body problem. In this formulation, we have two masses moving in circular orbits around their barycenter, and a third body of negligible mass, our particle, which is free to move throughout the plane. For the purposes of this presentation, we will be considering M1 and M2 to be the Earth and the Moon. We define a rotating frame so that the Earth and Moon appear to be fixed. Conveniently, the governing system of differential equations is autonomous. The equilibria of this autonomous system are called the Lagrange points. There are 5 of them: L1, L2, L3, L4, and L5. The first 3 are the collinear points, and the remaining 2 are the triangular or equilateral points. We restrict our attention to L1 and L2, but particularly L1. At fixed low Hamiltonian energy, phase space is separated into 3 distinct regions, sometimes called realms. The Earth realm surrounds Earth, the Moon realm surrounds the Moon, and the exterior realm occupies this external area. The gray region, in which no motion is possible, is called the forbidden realm. For the low energies for which this diagram is applicable, the realms are linked only by neck regions around L1 and L2. Because the L1 and L2 regions control transit at these energies, it makes sense to linearize about these equilibria to try to understand what initial conditions can and cannot transit. So we linearize and convert into a symplectic eigenbasis. We will get 2 decoupled canonical planes, a saddle plane and a center plane. So we fix the energy and then build out the geometry. The first thing to notice is that the forbidden realm persists under the linearized Hamiltonian. So we can say that the line P1 minus Q1 equals plus C is entirely within one realm, and that P1 minus Q1 equals negative C is entirely within another realm. This is helpful because if we want to understand what initial conditions that start out entirely within one realm could do, we just pick initial conditions on this line. Specifically, we start along the intersection with P1 plus Q1 equals 0, and then we pick initial conditions all the way to the boundary of the forbidden realm. Of course, P1 minus Q1 equals 0 is the boundary between the 2 realms. The origin in the saddle projection is the center manifold to the Lagrange point, as we'll see from the center projection shortly. The P1 and Q1 axes are respectively the stable and unstable manifolds to the center manifold, and they separate the 4 quadrants. Therefore, something that starts in the 2nd or 4th quadrants will not transit, because the geometry implies that they'll just bounce back into the realm from which they came. On the other hand, something that starts in the 1st or 3rd quadrants will hit both the P1 minus Q1 equals plus C line and the P1 minus Q1 equals negative C line. So therefore, these initial conditions must transit between the 2 realms. So along with the center projection, whose behavior is purely oscillatory, we now have a full picture of the transit and non-transit sets in the linearized region. The results will necessarily extend to the full equations of motion. What happens, however, when we introduce a time-periodic perturbation to the circular restricted three-body problem? Let's consider 2 examples of this sort of system. First, we have the bicircular problem, in which the perturbation comes from an extra mass, which in the rotating frame traces a circle around the origin. For us, this extra mass will be the Sun, so that we now have a model for the Sun-perturbed Earth-Moon system. Second, we have the elliptic restricted three-body problem, in which the Earth and the Moon are free to move in more realistic elliptical orbits. For the purposes of this research, we do not use the rotating pulsating frame sometimes used to make the Earth and Moon appear fixed in the ER3BP. Instead, we use an average rotating frame in which the Earth and Moon now trace periodic paths in the plane. As a terminological note, since these systems have a periodic perturbation, we often refer to the phase state of the system. The phase state of the system, which can be used instead of the time, is the time rescaled and modded to be between 0 and 2 pi. The Lagrange points don't persist in these sorts of perturbed models because they're relegated to being instantaneous zeros of the time-dependent vector field. They're not invariant sets, and they're not useful for analyzing transit. So what dynamical object can we utilize instead? Previous research, as well as our own investigations, have revealed that something higher dimensional, like a periodic orbit, tends to replace the Lagrange points in these perturbed models. As far as I know, and if I'm wrong about this, please shoot me an email, no one has yet thought of a name for these generalizations other than the dynamical replacement for L1 or something somewhat complicated like that. So we decided to start calling these trajectories Lagrange manifolds because they are invariant manifolds that generalize the Lagrange points. We do suspect that there are several classes of Lagrange manifolds, depending on the way that you're altering the circular restricted three-body problem. Under one perturbation, you'd get periodic orbits, but under two or more perturbations with incommensurate period, you'd get quasi-periodic orbits and higher dimensional sets of bounded orbits. Eventually, it might even be possible to approximate the Lagrange manifold in the real ephemeris. The remainder of this presentation considers the periodic orbit periodic perturbation case, leaving the quasi-periodic case for future work. Let's see some examples. In the sun-perturbed Earth-Moon bicircular problem, the L1 Lagrange manifold has a unique doubly looping structure and has period equal to the synodic month. In the Earth-Moon ER3BP, the L1 manifold is singly looping and has period equal to the sidereal month. Interestingly, the ER3BP L1 manifold is much larger in amplitude than the BCP L1 manifold. So, now that we have a Lagrange point equivalent, we need a method for determining the phase space structure in a small neighborhood of the Lagrange manifold. Linearization will not work, so we instead turn to Monodromy matrix calculation, a method which allows us to determine how particles near the Lagrange manifold evolve with respect to it after one period. We end up getting a linear, discrete map, not a linear continuous system, that represents where the particles will end up after one period. The initial condition of the Lagrange manifold at the current perturbation phase is the fixed point of this map. So let's say that our monodromy matrix is a linear elliptic hyperbolic map. Elliptic hyperbolic fixed points are the discrete equivalent of saddle center points, and it turns out that the monodromy matrices about the BCP and ER3BP Lagrange manifolds are both of this form. It also turns out that a quadratic Hamiltonian can be associated with the elliptic hyperbolic point using the following procedure. If we generate the continuous equations of motion of the Hamiltonian, and then obtain the one-period flow map, the Hamiltonian is defined in such a way that it yields a flow map identical to the elliptic hyperbolic point map transformed into its eigenbasis. This is quite useful because it means that in the vicinity of the Lagrange manifold, there's a Hamiltonian that's conserved under the one-period flow map. And this Hamiltonian is qualitatively identical to the Hamiltonian for the unperturbed system. So what does all this mean? It means that the transit structure in the perturbed system is a discrete version of the transit structure in the unperturbed system. When we switch into the symplectic eigenbasis in the unperturbed system, particles must follow these paths for all time, unless they get too far from the Lagrange point. But when we do the same thing in the perturbed system, we have a discrete map given by the monodromy matrix and a continuous system generated by the Hamiltonian that the discrete map follows. Because the Hamiltonians in the perturbed and unperturbed systems are qualitatively identical, the transit structure is exactly the same between the two models. But the real trajectory only has to match the linear continuous system when the phases align. So for example, under the discrete map, the trajectory must visit this point and then loop onto this point. But they do not need to follow the trajectory between these 2 points. They can use a different route to get there. Because our analysis was general, some form of this diagram must hold at every phase, but the specific eigenbasis and Lagrange manifold initial condition you're using will change, which would become apparent when converted back into position momentum space. As a result, it makes sense to restrict our diagrams to discrete points for fixed phase, particularly since this arises from a discrete map to begin with. These transit predictions hold for both of our models. Consider first these initial conditions in the BCP. The blue points should not transit when integrated forwards and backwards, but the red points should transit, as we see here, as we can see and remember from the previous slide. As you can see, the red and blue initial conditions both start from the moon realm and loop onto the Lagrange manifold, but only the red initial conditions, as predicted, transit to the Earth realm. The blue initial conditions instead return. Here's an animated version with slightly different initial conditions. This non-transit and transit orbit were generated very close to each other near the Lagrange manifold and then integrated backwards to the moon realm. And now this is what they look like animated and integrated forwards. As you can see, they shadow the Lagrange manifold right here very closely, but only the red trajectory ends up proceeding to the Earth realm. These transit predictions also hold in the ER through BP. In this example, I also demonstrate, however, how one can use any phase one desires. Here, we have blue non-transit and red transit initial conditions, but as predicted, only the red reach the Earth realm. But these initial conditions, as you can see, were generated for phase 0. What happens if we change the phase? Well, our predictions still hold. Our initial conditions are actually identical in the eigenbasis, but when they're transformed back into position momentum space, they clearly arrive and depart at different locations along the Lagrange manifold. In summary, the following process may be used to find transit orbits. First, determine an initial condition for the Lagrange manifold at some phase of the system. It can be whatever phase you find useful or convenient. Second, integrate the monodromy matrix. Third, if the monodromy matrix reveals that the Lagrange manifold is an elliptic hyperbolic point, create an eigenbasis from the monodromy matrix. Fourth, displace short distances away from the Lagrange manifold initial condition according to the geometry prescribed by the eigenbasis. This will yield transit and non-transit orbits when integrated. One of the key messages to take away from this presentation is that our research settles an important question regarding tube dynamics. Do the transit orbits and associated structures persist under time periodic perturbation? The answer is now yes. The theory we have shown is very similar, although you will need to use the Lagrange manifold instead of a Lagrange point. Our recent result, proved by Zhang and Ross, also showed that they are robust to dissipation. Taking these two results together implies that there is a bright future for further research in the field of transit orbits and transit dynamics. That was the presentation. Thank you so much for viewing. If you have any questions, feel free to reach out to me via my email or via Twitter, or simply to attend the in-person presentation. Thank you so much again, and I hope you found this interesting.